This is a topic that many students find a little bit difficult because you have to remember when we do the graphs of our inverse trig functions that there are restrictions. So remember that a function only has an inverse if it is 1 to 1. So we write that only 1 to 1 functions have an inverse. So that means we need to choose a section of the graph that not only passes the vertical line test to be a function, but it must also pass the horizontal line test so that we know that neither the x's nor the y's are repeated. So let's take a look at the graph of sine of x, and then we'll compare it to its inverse. And remember that we've got two notations. The older notation for the inverse function is the term arc sine of x. The more modern notation would be to use the -1 symbol for inverse sine of x. So we'll take a look at both of these on the same graph. And then this is something that you really want to commit to memory so that you can quickly come up with the restrictions. Okay, so let me make a rough sketch here of our sine wave. And remember from our unit circle that sine of 0 is 0. And it takes 2 pi units to complete a full cycle, 1 full period. So our sine wave, and hopefully this is now very easy for you to do. Our sine wave starts at 0, and then it reaches its amplitude of 1 at pi over 2. And at pi, the sine is back to 0. At 3/2 pi, we're at the -1 value. And at 2 pi, we've completed the unit circle, so we are back to the value of 0. So if we were going to graph the inverse of this function, we can see very clearly as we move across that this sine wave fails the horizontal line test. So what we need to do is to restrict a section of the graph that doesn't fail the horizontal line test. So we clearly can't go over any hills or through any valleys, but you can see that this section of the graph, if we stopped at pi over 2, that would pass the horizontal and the vertical line test. But then we would be leaving out all of those sine values that are below the axis. So what we do then, knowing that our sine wave is periodic, is we continue the graph backwards into the 4th quadrant. And now we can see that this section of the graph also passes the horizontal and the vertical line test. So now we can use this section of our graph that I've highlighted as our 1 to 1 section. So our restricted section, we want to get as close to the axis, as close to the origin as we can. So if we restrict the domain of the sine function from -pi over 2 to +pi over 2, then we have a 1 to 1 section of graph. And now remember what we know about inverse functions. Inverse functions are reflections across the 45-degree line. And I want to make it very clear that that point is not on the 45-degree line. So now what we need to do is fold that red sine wave over that 45-degree line. So let's use what we know about functions. This point right here is at pi over 2, 1. So we know on the inverse function that the x's and the y's trade places. And we know that this endpoint is at -pi over 2, -1. So let's use those as the anchors of our inverse function. So if we flip these values, so if we find the value at 1 pi over 2, the reflection of that point is going to go up here, and the reflection of this point is going to go down here, and we now have a graph of the inverse. So I'm not using graph paper here, so my points might not look perfectly spaced, but hopefully you've got the idea that we swap the x and the y. So our inverse sine function goes to pi over 2 down to negative pi over 2 as its range. And remember that we've spoken about that. So for our sine function, we restricted the domain to the interval from negative pi over 2 to positive pi over 2. And the range we were working with was from negative 1 to positive 1. So not surprisingly now, for arcsine, we ended up with a range that goes from negative pi over 2 to positive pi over 2. And our domain is negative 1 to 1. So notice that the domain of one becomes the range of the other, because in inverse functions we know the x's and the y's swap places. Okay, let's do the next two functions, and I think we can go a little bit quicker now that we've got a good review of inverses. All right, so here we're going to graph our cosine function, and we'll graph an entire cycle again as a quick review. We know that our cosine wave starts at its amplitude of 1. At pi over 2, cosine is back to 0. At pi, cosine is down at negative 1. At 3/2 pi, cosine is back to 0. And at 2 pi, cosine is back to its beginning point of 1. So here, let me try getting a nicer curve there. So we know that our cosine wave, of course, continues because it is periodic. And now we want to find our 1-to-1 section. So remember that we can't go over any hills because that would fail the horizontal line test. So basically you want to look for a section that goes from a maximum to a minimum without repeating any sections of the graph. So again, if I highlight a maximum to a minimum, and we want to be as close to the origin as we can. So do you see that we can take for cosine, for our 1-to-1 section, we're going to go from 0 to pi. And there's our 1-to-1 section of graph. And now again, we want to think, what will this look like when we reflect it for its inverse? We reflect over the 45-degree line. And this is a shape some students find difficult to remember. So our inverse sine function is going to be quite tall. If you're visual, and probably more than I am, you'll probably find this easier to graph. Here's what I recommend strongly. Look for the ordered pairs that anchor your graph. We know that the sine wave, this point 0, 1 on our sine wave, on our inverse has to have the point 1, 0. And look at our sine wave again. Here we've got the point pi over 2 comma 0. So let's look for the matching point on our inverse. Here's the point 0 pi over 2. So the x-intercept of one becomes the y-intercept of the other. And our endpoint was at pi negative 1. So of course on our inverse, we've got to go all the way over to negative 1 pi. So notice that the domain of one function, again, became the range of the other. So let's see if we can label those very quickly here. So for cosine, we limited the domain to 0 to pi, and that becomes the range on our inverse. And our range of our cosine graph went from negative 1 to positive 1. So for our inverse function, our domain is negative 1 to 1, and our range is 0 to pi. So it might be helpful for you to think of the unit circle, and why would we pick 0 to pi on the unit circle? Haven't quadrants 1 and 2 covered every possible cosine value? So that's a good way to remember that. As opposed to the sine function. For the sine function, we picked negative pi over 2 to positive pi over 2. So let me scroll back and add that so that if you watch this video, it'll be a complete review for you. So here's what we chose from the unit circle. Is it true that quadrants 1 and 4 cover every possible value for the sine function? So there's the visual way to remember your restrictions. Okay, one more to go. To save us some time here, we've already got a sine graph. And remember, of course, that we would have repeated branches. Did I say sine? I'm sorry, tangent wave. And if we look at just the first branch of the trig graph, even though there would be multiple, it looks like this first branch between the asymptotes of negative pi over 2 and positive pi over 2 is 1 to 1. It passes the vertical and the horizontal line test. So remember, this was our restriction for sine. It is also going to be our restriction for the arctangent function. So now we want to think what happens when we flip this over our 45-degree line. And interestingly, what used to be vertical asymptotes. Oops, I'm flipping this the wrong way here. I want to flip across. I want to flip this across the 45-degree line. So while our tangent function had vertical asymptotes, now our arctangent function has horizontal asymptotes, and they are at the values of y equals negative pi over 2 and y equals positive pi over 2. So again, finishing up here, for our tangent function, we're going to restrict our domain the same as we did for sine. From negative pi over 2 to positive pi over 2, our range for tangent was all real numbers from negative infinity to positive infinity. So on our inverse tangent, our domain is all real numbers. And our range goes from negative pi over 2 to positive pi over 2. And our analogy in the unit circle again. In the unit circle, you want to look only at values from negative pi over 2 to positive pi over 2. This semicircle of the unit circle represents every possible tangent. In quadrant 2, the tangents are just a repeat of the quadrant 4 tangents, and quadrant 3 is just a repeat of the quadrant 1 tangents. So when you do an inverse tangent problem, you want to remember to pick an answer between negative pi over 2 and positive pi over 2.